first speaker today is Viro from Peking University. We'll talk about Hempel pairs and Turaev Viro invariants.
Thanks very much for the introduction and also for the invitation. So today I wanted to talk about these Hempel pairs and Turaev Viro invariants. Hempel pairs is some object that's familiar to us in the profinite completion, which give non-profinite rigid examples. And the Turaev Viro are something from quantum topology, and I'll give more background of these kind of things later in this topic. But I guess rather, for this talk, what I wanted to consider is a direction in this profinite completion of manifolds over the in the past 2 days, we already see that the profinite completion and the profinite rigidity problem have been considered for different kinds of groups, and also in different kinds of manifolds, such as like yesterday, it's extended like Kähler manifolds. So for Turaev Viro, it's related to like 3 manifold topology, and the study is related to it. So if I take an overview of this profinite completion topic, then first of all, this profinite rigidity is, of course, one of the central and interesting problem in this direction. And I guess since I thought about this, for example, the profinite rigidity of hyperbolic 3 manifolds for some while, and I noticed that whenever you try to consider a problem in this direction, a natural thing to do is that so I guess a related question is, how do you say out a particular hyperbolic 3 manifold to try to give enough kinds of characteristics of this manifold, and eventually you can say, okay, this is that manifold. Perhaps the next step is trying to like translate these things into the profinite level, try to recharacterize those things by their profinite completions. So I guess this leads to this another kind of more general question, which I find magic especially in the study of 3 manifold topology. So in general, you can ask a question like this: is something a profinite property? So is something, let's say a 3 manifold property, can it be determined by the profinite completion of its fundamental group? I guess this question, the magic part of this question is not only about like for those successful examples where you can show something as profinite property, then it gives you some positive feedback. But also, even if in certain cases, like in the Turaev Viro case, which I'll discuss more, it has a somewhat more subtle answer. And in certain more general cases where even if you have some negative answer to such a question, then I guess so in studying such a question, you're forced to like relook at those collections of familiar invariants for in 3-dimensional topology, let's say, and maybe at first those invariants were not defined on the group's theoretical level. Maybe they are related to topological invariants, topological features of the manifold. And this will force you to try to characterize it on the fundamental group level and on this profinite level. And in doing these things, I find that it deepens our understanding of familiar invariants, and sometimes it can be inspiring. So I guess in this talk, I'll later talk about what about the Turaev Viro. But well, I can first mention some successful examples in three-manifold topology to the answer of this, and some of known profinite properties. There are many, such as the first Betti number and the torsion size of the first homology. But I guess some more striking examples are, for example, there is the property so-called the non-positively curved, being non-positively curved. I mean, this property itself, by definition, let's consider the all the orientable closed three manifolds. Then, by saying that such a manifold is non-positive curve, it basically means that it supports some Riemannian metric of non-positive sectional curvature in every direction. So this is at the very beginning, it was a purely geometric property, and nowadays we know that among three manifolds, being positive, non-positive curve, this is actually a profinite property. The basic reason is because of this. So first of all, because of virtual specialization, it tells you that the being non-positively curved can be characterized using fundamental group of three manifold. It basically tells you that first of all, if the manifold contains any hyperbolic piece in the geometric decomposition, then it must be non-positively curved. So the non-examples of this property only hold for a collection of certain graph manifolds. And for those graph manifolds, let's briefly this is always non-positively curved, and the sum graph manifolds there is some equivalent characterization. One of them, by virtual specialization, tells you that a graph manifold is non-positively curved if and only if it's virtually reverse, or it is it virtually embeds into some right-angled Artin group. There are some equivalent characterization, but those characterizations are not directly applicable if you want to check if it's non-positive. There are some other more concrete characterization in terms of the gluing data of these cipher fiber pieces. So there is some characterization on the fundamental group level. I guess details may be contained in a paper of Buyelo and Svetlov concerning virtual properties of graph manifolds. They give you a concrete description in terms of the topological data. And then after that, you can apply this result of I guess Wilkes has a series of three papers studying the profinite completion of graph manifolds. And actually, in the third paper, what he showed is that two graph manifolds are profinitely isomorphic to each other, then they must have a common finite cover. And that basically tells you that profinite completion among graph manifolds, a profinite isomorphism among graph manifolds, that is a commensurability class property. And being non-positive curve turns out to be a commensurability class property. So that basically tells you that for the graph manifolds, you have a satisfactory answer. Combining these two facts, you can actually say that this seemingly geometric property turns out to be completely determined on the profinite completion level. So that is perhaps one of the successful example where you can translate some known geometric property into a profinite one. And I guess there are some other examples. For example, being fibered or not, whether or not these three manifold fibers over a circle as a surface bundle. This is a familiar result by Andre. Yeah, and actually, so beam fibered itself, it has some group theoretic characterization in three-manifold topology. You can say that a three-manifold group is fibered if and only if it contains a normal finitely generated subgroup of infinite index. That characterization was due to Stalin, but in order to show that being fibered is a profinite property, you cannot apply that theorem directly. What you need to do is that you try to look at different kinds of twisted homology and try to extract the information from those homology and try to show that eventually you get this fiberedness. And I guess if you use invariants in his proof and then you try to push this argument further, eventually what you can show is that the combinatorial type of the so-called third norm ball. And the fiber faces, at least for hyperbolic three manifold, I think this this turns out to be a profinite property that is I think this is part of the ingredient where I used this to prove the profinite almost rigidity for the hyperbolic three closed hyperbolic three manifolds. So I guess this is sort of like the first step, and the next step you're trying to like characterize this twisted Alexander polynomials associated to that. If you have these two kind of ingredients, combine them, then you can basically rid of the entropy associated to the every fiber phase, and then use that you can bound how many hyperbolic three manifolds are there. So we can actually see that in order to say something about, for example, if we're interested in profinite rigidity problem related to three manifolds, then you can you can narrow the range down by finding more and more properties and trying to say that okay, these are profinite properties, and then if you're less lucky, then you only get a finite collection of possibilities, and if you're sufficiently lucky, then you might be able to at least solve the profinite rigidity in the, for example, in the relative case, in the relative sense. Okay, and then I guess among three manifolds and about three-dimensional topology, one of the questions which also Holger mentioned in the first day in his talk is that if among all the three-dimensional invariants, if we want to name one which is the most interesting, and we want to know if it is a profinite property, then how about the hyperbolic volume or the Gromov norm? Yeah, there are some. There are a list of similarly interesting invariants associated to three-dimensional manifolds, which are really challenging, and I guess I'll mention them at the end of this talk. But let's try to look at the case with hyperbolic volume. If we just imagine we just come across the problem for the first time, and we just want to do some brainstorm to tell if volume is a profinite invariant. There are a collection of facts which seems to be related to these things. One of them is this conjecture of so-called homological torsion growth conjecture, sometimes due to I should say conjecture. One of the versions was from Bergering and Venkatesh's paper, and there are some similar versions, some other versions from Tang Li's paper, and also from Luke's book about this L2 invariants. So. This is about the statement is that suppose you have a hyperbolic closed three manifold, and you consider exhausting sequence of finite covers. Or cofinal, which means that the fundamental the intersection of pi 1 of m I prime, this should be ID, and these are normal finite index. So the conjecture is that either for any or for some sequence like this, do you have this identity that when n goes to infinity, you look at the log of the size of the homological torsion divided by the m prime divided the covering degree. The conjecture is that the right hand side should be the logarithm L2 torsion, which is turns out to be the hyperbolic volume of m divided by 6 pi. You can see that if you can actually show a conjecture like this conjecture, then you immediately infer that the volume should be a profinite invariant, because the size of homological torsion, this is something that you can actually read off on the profinite level. But unfortunately, this conjecture stays open, and I thought about this for a while, and my feeling is that this conjecture might be even harder than the profinite rigidity problem. So that is at least one potential approach or some relation with some known conjecture. And related to this Turaev Viro, there is some similar version. Sometimes this conjecture is called the homological torsion version of volume conjecture, and there is another more classical volume conjecture associated to. At first, it was posed by Kashayev, associated to Legendre polynomial and the classical knots in S2 in S3, and then later there is an analogous conjecture which was due to Chen and Yang, Qintao Chen and Tian Yang, who posed this conjecture about 10 years ago. And the content of the conjecture is that, I'll review more about the Turaev Viro invariant, but basically there are different so-called different levels, and when the level goes to infinity, you expect that the Turaev Viro invariant at that level should go to for any closed or hyperbolic, let's say m. Orientable, maybe. Okay, divided by r, then they conjectured that this limit should go to volume divided by some constant. Turns out to be like 2 pi. I think this conjecture has been confirmed for. There is a version of Turaev Viro in the figurative in the cast case, and they first showed this conjecture for like figurative knot complements, and it holds true. And also they later I think they find Yang and Kalfagiani and Detri, they find some other collection of closed manifolds obtained by dim fillings of shadow link complement. I think they also confirmed the conjecture for that collection. So at least if we have some conjectural fact like this, it seems natural to try to see that if Turaev Viro are profinite invariants.
Can you define it?
Huh?
Can you define Turaev?
Yes, I'll mention it in a minute. Yeah. So I think I should provide some collection of background facts about this Turaev Viro invariants. So first of all, Turaev Viro invariants can be defined for any closed three manifolds. First introduced by So what you do is that given any closed three manifold, what you do is that you take a triangulation of it and then try to associate try to associate a quantity to each so-called status. So this is a general procedure is that admissible, so-called admissible status states. And I guess I'm not going to tell you exactly what the quantity is, but I can give you some sense of how the quantity looks. Like what you do is that you take a triangulation of the manifolds. Then what is called a status is that basically if you're given any r greater than or equal to 3, then you try to associate numbers I associate to every edge, which comes from a finite collection, try to associate and they have to satisfy certain admissibility condition, which looks like the triangle inequality to each of the face, like I plus j should be less than L, and there are some parity conditions associated to that. Then whenever you have a setting like this is called a state of this triangulation, and then from the state you can write down some algebraic expression involving involving a root of unity, and then that state sum will give you a Turaev Viro invariant. So basically, in order to define a Turaev Viro invariant, you need to so at the very beginning, you have to fix a root of unity. More precisely, you need to fix square root then whenever you fix some q, then the state some quantity, this expression is completely fixed, and then take the sum, you get a well-defined value, which turns out to be independent of the triangulation. That is called the Turaev Viro invariant. So eventually, the output is a Turaev Viro invariant, depending on this root of unity you choose, or q f you choose, and then for any manifold M, the value actually lies in the cyclotomic field extension of Q. Because this is defined by an algebraic expression, a polynomial in Q1/1, 1/2, then when Q changes by Galois conjugates, then the resulting value also changes by Galois conjugates. So if it were just given a description of the Turaev Viro invariants like this, then to make the notations more specific, so there usually people consider the different roots of unity. The most general, you can try to consider the root of unity to be of the form e to the I pi sum s divided by r. This r is exactly the notation r appeared there. That's the order of the root of unity, and this s is just supposed to be the and the s is co-prime to r. And whenever you have a fixed square root of unity like this, then what you get is and for specificness, I'll denote it as rs. So when r is fixed, and if you choose different s, usually the outcoming value just differs by Galois conjugates. So in a sense, if you're only consider about the algebraic structure of this invariant, then s which s you choose doesn't quite matter. That is a basic feature. But if you there are some analytic aspects of this Turaev Viro invariance that matters when you take the asymptotics. For example, this Turaev Viro invariance, as introduced by Turaev and Viro, at the very beginning, what they considered is the original version is basically TVR1, which corresponds to Q. This is e to the I pi 1 divided by r. That is the most natural one and has some meaning in physics, I guess. And then what Chen and Yang did is that they actually look at the Turaev Viro at these two. If you are plugging this the first root into the expression, here's I missed some. Turns out this is actually a non-negative integer, so you don't actually need absolute value. But the expression is basically like this. And if you plug in this root, this one root, then the expression here has actually polynomial the growth, and people have noticed this much earlier and didn't expect that there was a conjecture of this form at the very beginning. But what Chen and Yang did, and they I guess what they did is actually they wrote some computer program and then tried to just change this root a little bit, and suddenly notice that the growth root becomes some non-negative, some positive number, and they look at it more closely and notice that for figure 8 non-complex, the output is actually the volume of figure 8 divided by 2 pi. So they found that this is correct for making the conjecture like this. Some background story about the Turaev Viro and the relation with hyperbolic volume. But anyways, this is the Turaev Viro invariant is defined by fixing some root of unity or square root of unity. If you know some background in quantum invariants, Turaev Viro invariants are actually defined by representations of the quantum deformation of SL2, and this Q is exactly the Q here, those status, those IJK associated to the edges correspond to like irreducible representations of this algebra. So there are some backgrounds which are not. So first of all, the expression, as you can see from the description I gave here, so the Turaev Viro invariance is actually defined topologically instead of using a fundamental group information. It depends on a choice of triangulation, and also you do not see explicitly where the fundamental group comes into the play. Although there are some conjectures related to like when you have hyperbolicity, you should have like exponential growth, which reflects the features of the fundamental group. So that's this is some background situation about Turaev Viro invariants, and I should say that there is some other variant of this Turaev Viro when your R is greater or equal to 3 and odd, and in this case you also want your square root to have order R. Then because of that condition, then you for this situation, and if you look at the S associated to still coprime to R and even, and then for this setting, there is another parallel version of so-called Turaev Viro invariant, sometimes denoted as R and S. It turns out that if you know these values, and if you know the Turaev Viro of 3, 1, and 3, 2, then you can recover all the other Turaev Viro for at least the odd level Turaev Viros. So we actually have several variants of the Turaev Viro. This one and this one. The classical one is sometimes if you search in the literature, you will these are called the SU2 Turaev Viro invariants, and this series is sometimes called the 3 Turaev Viro. I think there are some interpretation behind, but it's not so. If you look at the definition themselves, doesn't exactly tell you what's the difference between SO2 and SO3. So it's just a name. So this is just a name for traditional reason. Okay, so to briefly summarize what we know about the Turaev Viro, these are some algebraic expressions when after you fix some root of unity, and it's defined as a state sum associated to a triangulation, turns out to be a homeomorphism invariance. The exact expression for the state sum is somewhat more complicated. So because of the time, I want to skip it, and I'll try to tell you some known classes of three manifold and try to see what's the behavior of this invariant for those known families of three manifolds. So I like to mention some facts which helps us to guess what's the relation or what's the answer to the profinite invariance of Turaev Viro. So the first observation is kind of seems to eliminate the question for all. It says that so actually people Turaev Viro invariant has some complicated expression which in principle for any three manifold you can compute it by using this expression. It's a finite sum, so you will eventually get an answer. But just based on the expression itself, it doesn't quite tell you for more complicated manifolds what the output value should be. So the manifolds where you can get simple answers, some basic example as Turaev and Viro did in their paper was S3 and RP3 and S1 times S2. So that's a very small collection of manifolds. And later there are some, I think that's due to Sokolov, and perhaps more special cases for by people earlier, that for length spaces you can actually find an exact expression determined by like LPQ, then you get an expression determined by P and Q. Anyways, the output is that there are length space only have a finite cyclic pi 1, so that's the same as profinite completion. So if you look at the exact formula, then you will notice that there among length space you can actually find some example which tells you this Turaev Viro determines on the actual homeomorphism time more than the fundamental group. But I guess this of course this example basically tells you that Turaev Viro should not be profinite invariant. And this seems to be this is a obvious negative answer to the question. But on the other hand, we know that length spaces are spherical manifolds. So so this counterexample seems okay. You might object that okay, this example doesn't count because these are spherical manifolds that doesn't. I mean. They're not determined by their pi 1, so it seems reasonable that that you get different values of Turaev Viro. How about those aspherical ones, where you have this topological rigidity? So pi 1 contains exactly the same information as a topological as a homeomorphism type. Then what should the outcome be? And I guess here it comes the interesting part, as it's common when you consider the profinite property question like this. So whenever you're given a concrete invariant defined in a certain way, and you want to decide if these are profinite properties, then immediately you are faced with several concrete questions. The first one is that if you want to give a negative answer by saying that these are not profinite property, then you'd better have a good collection of three manifold pairs which are not profinite isomorphic to each other. But I guess up to now, essentially we don't have not many such pairs. One is the Stips pair, but like torus bundle over circle with Anosov monodromy. That is one collection. And another collection is so-called this Hempel pair, which are like periodic surface bundles over circle. I think due to the classification of Wilks, what you can do is that you can create some more pairs of like graph manifold pairs. But essentially, the reason that they're profinitely isomorphic but not isomorphic was that there are some cyber fiber pieces which essentially come from Hempel pairs. So to summarize, essentially among three manifolds, what we know to be non-profinitely isomorphic, the basic reason is either it's Stip pair or it's Hempel pair, beyond these length spaces, the situation with Stip pair is that cannot be distinguished by any Turaev Viro. That means if you have two torus bundles which are profinitely isomorphic to each other, then if you try to compute any Turaev Viro invariant, the output value should be the same. And the reason is that actually Turaev Viro invariant comes from so-called the 2+1 topological quantum field theory. So basically to evaluate this for a surface bundle, you're taking a trace of certain matrix associated, and that trace can be explicitly written down for torus bundle pairs. and that representation you can directly see that if you want to evaluate the trace, the evaluation is the same as if you take like finite quotients and to evaluate. So basically for torus bundle over circle, this example doesn't give you. So this is just indistinguishable. Okay, so I guess the Turaev Viro was, I guess the Chen-Yang conjecture was part of my motivation why I wanted to look at this profinite invariance or non-invariance of Turaev Viro invariance. These are what is basically known at the very beginning when I started to consider the problem. Then the only left class is the Hempel pair class. Hempel pair are periodic surface bundles. So let's say the remaining question is how about Hempel pairs? They look like this. So you have a surface and you can glue it with this is usually genus greater or equal to 2, and you can glue it with FA or FB. And you can take FA to be some periodic mapping class F. Of order D, and you can raise F to some to some F to the K, something like this, such that the K is co-prime to D. Then you get a pair of. Then what Hempel shows is that this will give you a pair of manifolds which has which are profinite isomorphic, and these are all periodic surface bundle over circles. Say so. Speaking of the Thurston's hyperbolization, these are all H and 2 cross E1 geometry, and for this geometry, they also have a these are also cipher fibered manifolds, cipher fiber spaces with Euler number to be 0 and with Euler character of the base orbifold to be negative. That's our topological characterization of these things. And I think let me first state briefly state the results as a report of what we know of this question. So first is that there are non-trivial. Non-trivial means that their fundamental groups are different. Pairs with I'll omit some details. Actually, for basically, I think R greater or equal to 5, then you can find some examples for corresponding R. There are also So the brief answer to profinite invariance of Hempel pairs is that in general these are not profinite invariants, but for some Hempel pairs they are so they look so like each other, and they're not distinguishable by any Turaev Viro invariants. And I guess the key points or the challenging part of this project is basically that if you look at the Turaev Viro invariants, you will suddenly notice that even for very simple graph manifolds, it seems quite hard to get a closed formula for computing these Turaev Viro invariants for those. And also I tried to look up for knowing examples of Turaev Viro for cipher-fiber spaces. Finally, I found it in a dissertation of Hansen. I think that's a dissertation of his. After some search. But before that, I guess most formulas appearing in the literature was some general formula which describes the way that you can compute the final results there. And Hansen actually wrote down a complete formula which depends on the given any ciphered symbol, then you can write down a complete explicit formula involving a lot of multi-sums for the cipher-fiber space, and even for that formula, it turns out that the formula is so complicated, so the resulting value can be quite complicated. And then what we do is that you look into the formula itself and try to see if any kinds of assumptions can simplify your final results. And it turns out the basic underlying reason for this is that you can actually evaluate more concretely the Turaev Viro in certain cases. So if you're given a these are coprime, and you consider a particular type of cipher-fiber space with symbol like this. The G is a G symbol here, and the exceptional fibers all have the same order A, and with some twisting parameter Bn. Of course, you need the B1 plus this to be 0 to make sure of this E equals 0. Okay, so given this formula, what you can say is that first, if for all j, then you can evaluate at level A for any S, and the resulting value turns out to be quite simple. And that's the first thing. The second thing is otherwise. For any r greater or equal to 3 and A divides r, then you can evaluate this to be 0. And basically for any R, so if A is prime and R is co-prime to this, then there are some arguments of Galois invariance which ensures that this will be just an integer. So you will be able to get a complete answer. You have this simplified formula which give you answer like this. So I guess I'm out of time, so I stop here.
Any questions?
Are the Turaev Viro invariants defined for punctured torus bundles over the circle, for example, free manifolds with vectorial boundary?
Yes, for cast manifold there is also Chen and Yang introduced the version of Turaev Viro using ideal triangulations. So they are defined, and of course, whenever you have profinite rigidity, they will imply that this quantity to be the same.
That's okay.
Yeah.
Oh.
Yeah.
So if you take the punctured torus bundles corresponding to the steep pairs, then they become different.
Right. Like figure 8 not complement will the value will converge to the volume of the complement when R goes to infinity.
But for other punctured torus bundles,
it's not proved yet. The conjecture to be yes.
Any other questions? And let's thank the speaker again.